kids, Miss Block here. I'm so glad that you could join me today as we talk about minerals. I highly suggest that you take out your Earth Science reference tables and turn to page 16 so you can refer back to certain areas that I talk about and understand how to use your reference tables. The more you use them, the better you'll understand them, and the easier it'll be to use them when you're faced with a task. Again, you can always pause or rewind this video to watch again or to review something that you might have missed. Are we ready? Let's get started. So, what exactly is a mineral? And in simplest terms, minerals are the building blocks of rocks. So if I look right here at this sample of granite, you will see little specks in it, and each of those little specks are a different mineral. So the darker specks might be biotite mica, you might find some plagioclase and potassium feldspar in there, and quartz. All those mineral crystals grew into each other, and they are intergrown crystals in that granite. Now, granite itself is not considered a mineral. So why can we say that all minerals are rocks, but not all rocks are minerals? Let's look at some criteria that need to be met to be considered a mineral. So for starters, a mineral is something that's solid. It's not a liquid or a gas, has a definite shape and a definite volume. It also has to be found in nature, so it's naturally occurring. We just can't make it in the kitchen. It also has to be inorganic, which means that it's not alive or was never alive. That's the opposite of organic. It also needs to have a fixed composition or be crystalline, which means that it's made of crystals. Lastly, it needs to be an element or a compound, not a mixture. So let's look at some samples and see if we would count them as minerals or not. So if we look right here at this piece of amber, would this amber be a mineral? No. Amber would not be a mineral because it doesn't fit the 5 criteria. It is not inorganic. It comes from something that was once alive. It is fossilized tree sap. How about ice? Well, according to our criteria, ice is indeed a mineral, providing that you didn't make it in your freezer. It is solid, naturally occurring if we find it outside, inorganic. It's crystalline with that fixed composition, and it's a compound, H2O in solid form. Now you might be wondering, what gives minerals their particular properties? Well, the internal arrangement of atoms determines a mineral's properties. This is the most important thing that you need to take away from our minerals unit. Now you might be wondering, what exactly does this mean? This is like a big phrase. I'm very uncertain with what it's trying to say. Let's look at this example right here. Right here, I have diamond on the left and I have graphite on the right. They are both very different. One is a beautiful gemstone that is very, very hard, is used as industrial abrasives. Graphite, on the other hand, isn't very hard. It's we commonly find it in pencils as pencil lead. That's actually graphite in there. But they both have the same chemical composition. Why are they so different? Well, their atoms of carbon are arranged differently. So if we look here on the left, you can see how the atoms in a diamond are arranged in this crystal lattice. While on the right, we can see how the atoms of carbon are arranged in these sheets, giving them their different properties. So how the atoms are arranged will determine the chemical and physical properties of our minerals. That is the key. The properties don't determine the atoms. It's how the atoms are arranged to determine the properties. Now there are over 4,000 known minerals, but we keep seeing the same minerals over and over again. The reason is that if we look on the front page of our Earth Science reference tables, on page 1, you will see that the largest percentage of the crust happens to be oxygen and silicon. So it should not come as any surprise that the large percentage of minerals that are found on Earth's crust are going to be made of oxygen and silicon, and they're actually known as the silicates. And they have this structural unit, known as the silicon-oxygen tetrahedron, a 4-sided shape. So we got 1, 2, 3, and then it's sitting on the 4th side. Silicon and oxygen make up a lot of minerals. In fact, quartz, which has silicon and oxygen, is the most abundant mineral on the Earth's crust. We're going to now talk about page 16 and the various properties that we can use to classify our minerals. All right, so you might want to turn to that page if you haven't already. So let's look at the first property, luster. Luster refers to how a mineral shines or reflects light. When we talk about luster in earth science, we're going to be talking about if it's metallic, looks like a metal, or non-metallic. It can still be shiny, but it doesn't look like a metal. So we would say it has non-metallic luster. Metallic versus non-metallic. This is the first way that we organize our minerals. We separate them based on their luster. So the minerals found at the top of page 16 have metallic luster. They will look like metal. While the minerals found on the bottom of the page have non-metallic luster. They do not look like a metal. Hematite is unique. It can look, I have metallic or non-metallic luster. Next, we have streak. Streak is the color of the powdered residue of a mineral. It is more reliable than the color of a mineral. Mineral color is a poor classification feature. Many minerals can be the same color, or a single mineral can come in many colors, like quartz. So we try to go with the streak. Streak is found by taking the mineral and dragging it across an unglazed porcelain plate. It will leave behind a color. Even if that mineral comes in many different colors, the streak will always be the same. Streak is unique in the fact that they put it in the distinguishing characteristics. So you would need to read through here if you had a mineral that had a streak to see what your possible choices could be. Next, we'll look at hardness, and this is the resistance a mineral has to being scratched. We measure hardness using the Mohs hardness scale. So if a mineral will break down easily or is easily scratched, it will have a low number on the Mohs. If it has a high number, it is not likely to be scratched, like diamond. Hardness is found here in our reference tables as well. We go from low to high hardness right here. And we can also see it again from low to high right here. So we separated it again into metallic versus non-metallic. Cleavage and fracture refer to how the mineral breaks. Cleavage is to break along zones of weakness, while fracture is when it produces an uneven breaking surface. Quartz will demonstrate fracture, or these jagged breaks, while muscovite mica, feldspars, halite, and calcites, they will have these zones of weakness, and they might break off in thin sheets or produce a staircase type look. We can find cleavage and fracture here on our reference table, and they'll be checked off. We can also see some special things with color right here, again, a poor indicator, composition as well. This will indicate if it's a silicate or not, because it will have that Si for silicon and that O for oxygen. In case you forget what your element symbols mean, they've included it along the bottom. So S is for sulfur, not for silicon. Si is for silicon, and O is for oxygen. You can see also then what the mineral is. I hope this was helpful, and I hope it helps you with your lab. Take care. Have a great day. Bye-bye.